Black hole orbit. Our problem is we're given a table of values representing the position of a star in meters as it orbits a black hole. Our data points are taken once per day, so delta t is 86,400 seconds. We know the star's mass, although since gravity is the only force involved, the mass of the star won't end up making a difference in our calculations. A black hole is said to be at a position that we know, and using the star data and what we know about gravity, find the mass of the black hole. So we have a list of position, and now we're going to process the data to find physically meaningful values, like velocity. So we compute velocity using finite difference. That's what the code on the top right does. It goes down the list, computing delta x, dividing by delta t to get velocity, and makes a new list with velocity values. We can compute dp dt, the derivative of momentum with respect to time, by using the same technique, finite difference. So the code here, middle right, chooses 2 points, 2 consecutive points from our velocity list, v init and v final, multiplies both by mass to get momentums, and does finite difference. And so then we have those vectors, but we decompose it into parts parallel and perpendicular to our momentum using this projection method available using Python. So that's what this top part of the code does. And then the second is Newton's second law says that we should equate all of these f-nets to their respective dp/dt counterparts. And Newton's second law says that all of these are equal. So that's what that code does. And then we can run a simulation in VPython. Yellow represents our f-net vector, black is the parallel component, blue is perpendicular. So it looks like that. We have enough information that we can calculate the mass of the black hole. So by Newton's universal law of gravitation, the magnitude of the gravitational force is the mass of the star times mass of the black hole times gravitational constant over distance between them squared. And so you can rearrange this using algebra to find an expression for the mass of the black hole. And we don't just want to do this at one point, but we want to continuously take a running average so that we can get a better approximation for m. So here is my implementation of a running average. That's just math and computer programming. And using this, our average value for m, the mass of the black hole, is 4.378 e31 kilograms. So what does this all mean? F-net, which we said before from gravity, is mass of star times mass of black hole times gravitational constants over distance squared. And this force on the star is caused by the presence of the black hole. So that's F-net. dp/dt is a measure of the rate of change of the star's momentum, and momentum is an intrinsic characteristic of all objects, and is equal to ma in this situation. So we set them equal by Newton's second law, and so this is where we get that since m is right here, and m is right here, m is on both sides of this equation, and F equals ma. F equals ma, mass drops out. All objects, regardless of mass, are affected by the black hole in the same way. So what if the black hole was replaced with a different black hole that generated the same star data? Could you tell the difference? And my answer is no, because the only parameter that affects the star's motion is the mass of the black hole. And if the motion doesn't change, then the masses of the two black holes must be the same, and you wouldn't be able to tell the difference. It doesn't just work for black holes. If the black hole were replaced with a large star of the same mass, the motion of our observed star wouldn't change. All that matters is the mass. So, thank you. That's my presentation.